So for example, in the first image, there is mode 1 loading. So voids are growing in that direction, and then when you break it, then you see the dimples or the fracture surface, which will look like that. And in shear, because the voids are growing in different directions, you will see elongated dimple, so oriented in some direction. And this orientation can be because of loading, and it can also be because of a pre-treatment which is given to the sample before fracturing. So for example, if the plate is rolled in any direction, then the dimples, because the grains are oriented in that direction, dimples will be oriented in that direction also. And in this picture you see how the voids are developing, and you will have, so in this picture you can see there are voids everywhere. Very close to the neck area you have a lot of them, and you have coalesced voids here, and this appears to follow the shear direction, this whole coalescence. But you have coalescence at other locations as well, but they have not increased to the critical size, and whichever obtains a critical value beyond which it cannot grow further, then it will just start cracking in that direction. Okay, so when you have voids like this and the crack opens up, then all the voids, those who have coalesced, those who have not coalesced, will break, and because of that you will get a roughness. So this roughness can be a measurement of how much ductile the material is. If the roughness is too small, it means that void were not able to grow or coalesce. So it is really, the components which are used in real life are neither ductile nor brittle. They are somewhere in between. So you don't see a perfectly ductile material unless you are operating at high temperature. And there are also different materials can show a little bit of brittleness. So the signatures which you get on a piece of material which is broken can be at different scales, and that scales also we have discussed. Okay, so when you look at with your naked eyes, so on a tensile specimen you can see these things without any microscope. So if a cylindrical tensile specimen breaks, then you will see a fibrous zone in the middle, where, so you try to correlate that with the region which was shown in the previous slide. So a lot of bigger voids have broken here. So this will be very rough here. Okay, and once this has happened, so it has achieved the critical size, then the fracture will happen in the shear direction. So you will have a radial zone, and after that you will have a shear leg. So I don't know why I'm drawing it, is already there. So you have a radial zone where the crack propagates. Okay, so the fibrous zone is the place where voids are coalescing and creating a crack. The crack initiates that. Then it propagates in the radial zone, and you will see these lines which will be representing where the crack has come from and where it is growing. And that helps in post-mortem of the samples in real components to obtain where the crack origin was. So by tracing back these lines, you can find out where the crack might have originated. And if you follow these lines, you will see a fibrous zone if it was a ductile fracture, and some other zone if it was a different fracture. And then you will have shear lip zone where the fracture happens in the shear direction. This shear lip zone will be of different sizes if the material is showing a different property. So for example, in glass, when you break a glass, it is not safe because it can cut your hands. Why? Most of the reason on a broken glass is flat and it is blunt and it will not cut you. But the problem is the part which cuts you is the shear lip, which is very small in size. Okay. So it obtains. So this dimension is very small in glass, and because of that, you will get a very sharp in a very small dimension, it will achieve an angle of shear. Okay, and rest of the part will be blunt in a broken glass. So this is what will cut you. So this you can see from naked eyes, and when you look at it under microscope, scanning electron microscope, then in the fibrous region you will see these dimples. Okay, and you will see different sizes of dimples. And so, for example, this one is a big one, and you also see some lines inside it here and there. They are dull lines, but there are a lot of lines inside, and those are the markers of coalescence of different voids. So different voids are joined together. Boundaries are still there, which you will not see in smaller dimples. Sometimes, if you either do in situ fracture, or if you do a very careful preservation of fracture surface, and when you break it, you can also find the particle from which the void must have nucleated. So you can see a lot of times you can find carbides sitting inside these broken dimples, and because these dimples are rough, they will not fall. And you can also see sometimes oxides, but I'm not so sure if the oxide is there from the beginning, or when you break it then it gets oxidized. So these dimple sizes can be measured like you measure grain size. Okay, so grain size is also, so grains are also of not exactly same size in the material. So you take either linear intercept method or some other method. You can take image segmentation method and try to find out the average grain diameter. So similar things you can do on these pictures, and you can find out the average dimple size, and this average dimple size will be telling you how much the material, how ductile the material is. Okay, because it is a fractured surface, and it also is very important where do you take the picture. If you take the picture close to the crack origin, then in that case it will be telling you more about the material's property, because if you are far away from the crack origin, then the loading conditions might have been different. Okay, so dimple size has been related with the fracture toughness value, for instance, or yield strength value, or different other mechanical material properties. So dimple size is also used for quantitative fractography. Average dimple size has a correlation, although it is empirical. There is no theoretical relation of dimple size with the fracture toughness property, but empirical relationship is there, and that relationship is very strong. So it is undeniable, and it is a fact that dimple sizes can tell you about how ductile the material is. It cannot tell you how brittle the material is. If there is a brittle fracture, you will not see dimples. What will you see? You don't know. So that will you see. What will you see? So in this schematic, you see that how the dimples will be looking because of different loading conditions. So for example, the first image is talking about you have mode 1 loading in that. Okay, and in metals you will see dimples which are not oriented in any direction if there is no rolling involved before. And similarly, in mode 1 loading you see dimples of this size at the uniform strain. So this is just a representation that it is opening up in one direction in mode 1. So you will see dimples on both surfaces of the same size. In shear you will see they will have a exactly opposite orientation. Okay, because the upper surface is moving in a reverse direction to the lower surface. So this is what you will see, and in mode 2 you will see something like this, and so on. So this is schematic. I'll share you this, and in a complicated loading you can see different orientations of the dimples, and this can tell you not exactly how the loading must have happened. That much information you sometimes have, because if you have a broken piece of a component, you know where this piece was. So you know what kind of loading must have been there. We are not that blind in having the initial conditions to understand how the fracture must have happened, but in some cases we don't know. So for example, if a debris hits the space shuttle and then you have failed component, somehow you get it, then you don't know what, in which direction and what kind of loading must have happened there. Also in the military applications, when you have missiles hitting and all those things, then also you don't know the initial conditions, so how the loading must have happened. Okay. And then there are different features inside the microstructure. Some of them we have seen earlier. So for example, you have grain boundary, which can divide the fracture, which does divide the fracture into two categories. One is intergranular and another is transgranular. When a crack follows boundary, then it is intergranular. And so in ductile fracture, what do you think will happen? Intergranular or transgranular? Or in fatigue, what kind of fracture do you think will happen? Intergranular or transgranular? In fatigue. In fatigue, usually you will see transgranular fracture. It is not very sure, but mostly these things are true. Okay, so in brittle fracture, sometimes you have a situation where grain boundary is brittle and grain is not. Okay, so grain boundary is usually amorphous. It will have a lower strength, but the strength increases. It changes. It varies. Okay. So, for example, if you put carbides or oxides or dispersions on the boundaries, you can't deliberately do that, right? But it is also not that difficult to do. So, for example, you know that these precipitates will precipitate at a higher energy areas. So, you know that whenever precipitation happens, it will happen at the boundaries. Some of them will not be happening at the boundaries, and that is a complicated situation. So for example, if you have chromium in steel and you have vanadium also in steel, so then chromium will take all the grain boundary. It really is not that there is no space left in grain boundary, but all the chromium will precipitate on the boundary. Okay, and vanadium has a tendency not to go on boundary, but it will also not form inside the grain where there is no inhomogeneity. So it will try another inhomogeneity, which can be in the form of lath interfaces when you have tempered martensite. Okay, and it can form at the dislocation barriers, slip bands, and other inhomogeneity twist boundaries also, twist and twin boundaries. These are also the regions where some of the precipitation can happen. Okay, so we will not discuss what twist boundary and what twin boundaries are and how they form. For that, there are some videos available on YouTube. You can follow that. So, for example, in the course of MM504 phase transformation and alloys, there we have discussed how twist and twin boundary develops. Okay, but the essence of that is, when we try to imagine grains in a microstructure, then we know that orientation is changing. Okay, whenever there is a boundary. But that's really not true, because in nature nothing happens in discrete manner. It's not that suddenly there will be a change. It's a gradual change. Okay? So more than 10 to 15 degree orientation mismatch will create a boundary, which is called grain boundary. But you will have a gradual change in the orientation. Okay? And that can happen because of dislocations sitting in a fashion. Okay, sometimes dislocation, they make a network, and it really looks like a network. Okay, it's like a net, fish net. Okay, but in 3 dimensions. So why? Because we have seen that forces on dislocation are minimum when either they are at 45 degrees to each other or 90 degrees to each other. Okay, so they will try to arrange themselves in this order, because here the force is minimum and here the force is minimum. So all the dislocations, if they can move, then they will move, and then they will find a place. Well, When you are applying stress, they are moving. There is no need to stop. Okay? There is a tendency for the dislocation to move, but if, well, Pern-Levallois stress and other things are different, then it will be a different case. Not all the dislocations will be moving, but we are talking about dislocation in a grain. Okay? So for a grain, average critical result shear stress is crossed after some time because orientation is not much different. So for all the dislocations, CRSS once it is crossed for all the dislocations in one grain. So now they are moving. They have no reason to stop as long as there is a stress. Okay? And then you increase the temperature because you want to do recovery or you want to recrystallize. Okay? So you have forged your specimen or your component, and then you want to leave it at a relatively not very high temperature, which is called, so there are different heat treatments, I'm sure some of you know, right? Annealing, normalizing and things like that. One of the heat treatment is stress relieving annealing, okay? And that is done at moderately high temperature, not very high temperature. Annealing is also called sometimes solutionizing because you put all the things, whatever you have in your khichdi, to a solution, right? So in steel, you have carbides, ferrite, martensite, pearlite, histite. All those things are there. When you do annealing above the AC3 temperature, then what are you doing? You are putting them in austenite phase, and in austenite phase solubility of carbon is more. So all the precipitates will dissolve there, and you will have one phase, which is FCC. Nothing else will be there unless you have oxides in it or inclusions. They will not get dissolved, but everything else will dissolve. So this is why it is called solutionized. Okay? Stress relieving annealing is basically, the aim of that is not to change the microstructure. Okay? If you do solutionizing, if you put your steel to FCC, then the whole microstructure is gone, and you will have to create a new microstructure by giving another heat treatment. So defining your cooling rate. So either you cool it fast, slow, or when you solutionize, then you do a lot of beating. So you increase or decrease the grain size. Okay? So that is one way of deliberately putting precipitates on the boundaries. So in iron carbon system, alpha plus austenite. So if you heat your steel above this temperature and you put it somewhere here, then all these phases are gone, and you don't have carbon in it, so all the precipitates are gone, and everything is in one solution. Okay? And then you want to make a new structure, and it is solid, it is not liquid. Okay? So it's a solution, but it's a solid solution. And then you want to precipitate things out at the boundaries. And if you want to increase the strength of it, so then you want to decrease the grain size also. Okay? So if you cool it a little bit faster, not that faster so that it becomes martensite, a little bit faster, which is normalizing, in that case you will be making smaller grains, okay, in comparison to what you would have made by doing a slow cooling, by annealing. Okay? So furnace cooling. So you will be making a smaller grain, and then precipitation will occur at these boundaries. Okay? There is no other high energy area for the precipitates to come. Right? So that will happen apart from twist and thin boundaries. But if you beat it here, if you do forging, for instance, hot forging or hot rolling, then you are decreasing the grain size here in FCC. Okay? And then when you cool it, you give the same cooling rate which you have given to this one, then you will be further decreasing the grain size. So in this case, the grain size will be even smaller. Okay? And depends how fast you have cooled or how much you have beaten the steel, you will have a lot of strain also inside the material, although it is at high temperature. So if you cool it slowly, those strains will go away. Okay? Because while you are beating at this high temperature, what is happening? Dislocations are moving, but also recovery is happening. So all those mechanisms which can annihilate a barrier, which can dissolve dislocations, or which can provide a different path to the dislocation, all those things are happening. Okay? So this is a place where you have strain hardening as well as recovery going on simultaneously. And if recovery is finished, then recrystallization will happen. Okay? So before that happens, if you cool it, and if you cool it faster, then you will have a lot of strained region inside the grains, and that slowly will recover even at lower temperature. And when they recover, then you will have dislocations which are inside, and now the stress is gone. There is no stress because you are not beating it. So those dislocations are there, and they are also not at room temperature while you are cooling them. Okay? So what can happen is that dislocations have the help of vacancies with it, so they can move by climbing. They can't glide because you don't have stress, but they can climb because you don't need stress for climbing. Okay? So they will climb and they will arrange themselves in this order so that they can minimize the strain energy which they have already. So basically what dislocations are doing, they are trying to accommodate the strain they have with the minimum distortions possible. Okay? And this is called a cell structure, also known as polygonization. Okay, so dislocation arrange themselves in an array so that it looks like a polygon, it looks like a network inside. So when you have, for instance, an extra half plane here, okay, then you have a lot of distortion. Okay, and you see that here there is a change in angle. And if I put another dislocation, so suppose this becomes an extra half plane below that, and this becomes an extra half plane below that, then I am creating an angle there, an orientation mismatch. Okay? Yeah? So this becomes a tilt boundary. Similarly, if you have twinning happening, then you will have a twin boundary. Okay? So these type of boundaries can happen because of the arrays of dislocations which are there, and that signature is also seen when the sample is broken. So you see the first image that is talking about tilt boundary, and the lower one is talking about the twist boundary, and you have these kind of markings. It really will not look like this, it will look like this, it will look like feathers. Okay, and these are the representation of that. Okay, and what are these, which looks like rivers, also called rivers, river lines. So there is no dimple here, it's a brittle fracture. Okay, so void formation is not there. Even if it is happening, they are not the one which are deciding the fracture. So void nucleation can happen, but before they can grow, because the growth requires more amount of strain accommodation in the matrix surrounding the void. If the matrix is brittle, it will break. So you will not have enough deformation for a void to grow. Okay? So once the matrix is breaking and material is not able to take more load, it will break on those planes where least number of atoms are available. Okay? So it is exactly opposite to the slip system, where slipping happens on a highly dense plane. Brittle fracture will preferably happen on a least dense plane. Okay? And these planes will have different directions in different grains. Or if you have a twist boundary or tilt boundary, then also you will have a mismatch between the two planes in the same grain, where you have same least packed planes. Okay? Orientation is not changing much, right, inside one grain, but there are more than one lattices in one grain, right? So in each lattice you have a different plane, and these planes, as long as there is no mismatch, there is no twist or tilt boundary, they are on the same plane, so crack is propagating. And then you have a mismatch, so another crack has propagated on a different plane, and these two have to join now. Okay? and because material is not holding much, so it will just join and you will have a step formation, and this step formation will be prolonged to a certain distance, and that looks like a river pattern, especially when the river forms a delta. Okay. And this is how the brittle fracture will look like, the real brittle fracture. So you have these river lines, okay, and then you have step formation. These are called cleavage tongues. These are cleavage tongues, okay. And can we do something about quantitative fractography here? Can we relate any of the dimensions to the fracture toughness of the material in this case? Maybe the length of the river line, the step of the cleavage tongue. Any signature can be used to find out or relate with the fracture toughness? I am not aware of it. So far, no quantitative fractography work has come across me which has related the signatures of brittle fracture to the material's property. It sounds very weird. Why not? But then you try and do it. Okay. So far this has not been correlated, but maybe fractal dimension is one thing which can be used, and so the work on fractal dimension has shown different relations. So there is no consensus in the literature. People have found fractal dimension to be related with fracture toughness or mechanical property of the material. They have found it to be inversely related to the material property, and they have also found that it is not related with the material property. Okay, so fractal dimension actually matters when you have ductile fracture. Then in that case the correlation is very strong. But when there is a combination of brittle fracture and ductile fracture, then there is some problem. And when it is completely brittle fracture, then also there can be a different correlation or not. I am not so sure of. Okay. So now let us come. So we have discussed ductile fracture, we have discussed brittle fracture. What else are we missing? There is one mode of fracture in which you get very strong fractographic information, very strong, and you will find maximum literature of quantitative fractography in this type of loading. Can you guess what kind of loading is that? No idea. It's fatigue. In fatigue, you have a very strong signature from fractography, but these you will see at under scanning electron microscope. When you look at optical microscope, then also you see certain signatures on a sample which look like this. Okay, and these are called beach marks. These are not striations. These are beach marks which will be visible under optical microscope only, and whenever they are visible, you should be very confident that it's a fatigue fracture. If it is not visible, it is not a guarantee that it is not a fatigue fracture. Okay? So the name should have been sandy beach mark, because on a non-sandy beach you will not get these lines. Okay? So these are called beach marks, and when you look at the sample under scanning electron microscope, then also you see certain lines, but these lines are not vague as beach marks. These are very good representation of what is happening in the material. So each striation line is a representation of one cyclic loading. Okay, and there is no empirical correlation or nothing. This is the fact. This is the reality. Okay, and you see in this picture that they have done it in controlled manner. So they have changed sigma by sigma max at different number of cycles, and they see that different spacing of striation is obtained. Okay, and you see that for each, so you can count how many number of cycles it has gone through if you can count the striation lines. But the problem is, if your component is big, you are looking at scanning electron microscope and it will take years for you to count it. Okay, so then it has to be correlatable from a small area to a bulk component. So if you take a 1 micron into 1 micron in a small area, and then you find out or count, rather than counting how many number of striations are there, if you count the striation spacing or average striation spacing. So striation spacings will change because you will have different stress conditions. That is clear from that. If you change stress conditions, then you have different striation spacing, right? So in a cracked specimen, when you are doing fatigue crack growth, either in laboratory or your component had a crack already, and then in aircraft it went through fatigue cycle and it broke. So you began with a crack. Then there will be change in constraints from the surface to the center. That will cause different stress conditions. That will cause different striation space. Okay. So you have to find out average striation spacing, and that can be correlated and has been correlated, and it has been found that the area fraction of striation spacing is proportional to delta K by E. Okay, this is 6, not sigma. This is 6. Okay. So the striation spacing is proportional to the amount of stress intensity factors you have applied, change in stress intensity factor, and that is just normalized with elastic modulus. Okay, it's not that elastic modulus has a role to play in that, because on the left hand side you have a fraction which has no dimension. So other side also you should have a dimensionless property. Okay, and because you see 6 and you see a curved equation mark, it is an empirical equation. Okay, there is no theory related to this. So these are some other examples. So that is a controlled environment where you put a sample, load it, and then you try to correlate and understand the physics how striation forms. But in reality, you will see striations in a curved sample, and then you have a lot of different microstructural features. Okay, and so you will have something like this. So you have to take a small area and then measure at different locations and then find an average of that. Very interesting work was done in the conference somewhere in 2016, where they were trying to investigate how the fracture has happened, and some complication appeared. I really don't remember the whole work, but some complication appeared because the microstructure had pearlite in it, and it was not really possible to differentiate between striation markings and pearlite, and some striation markings were found on pearlite. So very fast number of cycles or some other reason which created a very small striation spacings, which was missed initially, and then later they found that they were trying to find out how this thing has broken, and they found that it was because of fatigue, but after a lot of investigation. So these investigation, for example, there was a aircraft called de Havilland Comet, which was earlier than McDonnell Douglas. So, and that company was also good, and that flight was doing well, but then they had like 7-8 crashes. Okay, and because of those crashes their company went bankrupt, and there was a different agency which was involved in investigating why that fracture has happened, and they took the whole aircraft, they put it inside water so that they can create pressure on it, and then they did loading of the components, and they found that it was happening because the windows, one of the reasons was that the windows were in square shape, and that square shape is causing a lot of stress intensity to appear on that. How much time do we have? And this is an optical microstructure of intergranular fracture. Transgranular fracture will be very simple, but in this case you see that the crack is following the boundaries, right? It is not a very happy situation. If for the same material property, if a crack has to follow transgranular path and an intergranular path, then by thermodynamics it should go transgranular because the path length will be smaller than that, right? So if it is following grain boundary, it is taking a longer path, and that tells you that the path must be easier. Okay? So this usually happens when you don't have manganese in a steel. So you have iron sulfide formation, and that iron sulfide forms an eutectic, and that becomes very viscous at the boundary. So it acts like almost like a liquid on the boundary. And then if you have a crack in it, then it will propagate. This used to be a problem long back, and then it was solved by adding manganese. So manganese have more affinity to make sulfides, so it will take sulfur, it will make MnS, and that is not going to act like FeS does, and therefore you will not have that problem. Intergranular fracture also happens when you have carbides forming at the grain boundary, and when you have, for example, chromium carbide formation, then chromium is absorbed from the surrounding area. Okay, so all the chromium and also carbon will go to the grain boundary. So you will have a zone which is depleted in chromium adjacent to the boundary. So there you will have a lower concentration of chromium. Okay, so this is also causing a local change in mechanical property, a gradient of mechanical property, and these carbides help. Chromium carbide is not a bad carbide. Okay, it pins the grain boundary. If you have a carbide which has formed on the boundary, then that is connecting the other grain. The grains from the other sides, they are connected by these carbides, because a part of carbide is also there in the grain number 1, grain number 2, and also on the boundary. Okay, so when the temperature increases, then what will happen? Diffusion will increase, so more carbon will go, more chromium will go, and these carbides will grow in size. So coarsening will happen. Okay, after coarsening, now what happens? After equicohesive temperature, grains are stronger than grain boundary. So grain boundary become fragile, and therefore you have grain boundary sliding and those kind of mechanisms by which strain is taken. So we are talking about leak. Okay, so this is elevated temperature deformation where these things are happening. And so what is happening is that to accommodate strain, two grains are either the grain boundary is migrating, okay, or the grains are sliding so that the strain is accommodated. Okay, if you want to stop it, if you allow it, then the material is acting as if it is a very viscous solid. Okay, so it will just flow like anything, it will deform like anything. Okay, if you want to stop it and give more strength to your material, then these carbides will help, because these carbides are connected to the grain, so they will not allow the slide to happen. Okay, but it depends at what temperature you want to put your specimen. So chromium carbide will coarsen and it will dissolve. Many of the carbides will dissolve. So titanium carbide will dissolve at high temperature. That's why you don't put titanium carbide in, for example, 9-1 molecule. Okay, so but if you put titanium nitride and carbide, they are a very good grain boundary holders. They pin the grain boundary. Okay, But if you want to go above that, then you need to use some dispersions which can come at the boundaries. Okay, so yttrium oxide and things like that are used to hold the grain boundary. But then the question is, how do you put deliberately those particles on the boundary? By physics. Okay, so if you have rice and if you have a lot of unwanted particle in rice, how do you separate them? That's a course on mineral beneficiation. How do you do that? You take a soup kind of thing and then you just move it and then they will separate. Okay, so when you do mechanical alloying, when you're doing ball milling, in that case also different sizes of particles will go and find their own places based on their densities and all, right? So I think this is fine with the presentation. Oh, we have another fracture surface of intergranular fracture of an embrittled cast steel. So this was a so this is a microstructure. This is not a fracture surface. This is not a fracture surface. Okay. Fracture surface will be when these two pieces are broken. Then you look at that surface. That will be fracture surface. Okay. This is a microstructure. When you look at fracture surface, that is a fractograph. Okay. And the fracture surface of an intergranular fracture will look like this. So here you can't really see what is that. Okay. But I think the part is removed in this case. You will see grain boundaries also in this case, and you have, so what you see here is that this is one grain, okay, and then you have a step here. This is another grain. Then you have a step there, because the boundary is, it has broken from the boundary, okay, and the boundary is not on one line. So you will have, and then you can imagine that here also the surface roughness is telling you something about it. But better than that, grain boundary size. So grain size is telling you something about it. Okay, so grain size can probably be correlated with the fracture toughness in intergranular fracture. At least that can be done. Okay. So good then. I believe quantitative fractography is over. We will not go in much detail, but if you want to, you have to choose one topic. So either one of the loading conditions. Okay, you can take monotonic loading, cyclic loading, creep, and you can take fatigue, you can take any other type of special cases and just write one page on the quantitative fractography, not qualitative fractography. Don't go in basics that how they form and all. Talk about quantitative analysis, how the measurement is done and what is shown in the literature, how that is related. For example, in ductile brittle transition. Okay, so we have discussed about Charpy test, right? So BCC alloys will show a different energy with different temperatures. We have also spoken about the fracture, so stress intensity factor, how that changes in the temperature of ductile brittle transition for BCC alloys. Okay, so what is happening here in the lower shelf is that you apply a load and it breaks. Okay, then you go in the ductile to brittle transition. What happens first? There is a plastic deformation, a little bit of plastic deformation is happening on the lower part, and then depending upon how many number of carbides are there at the crack front, that decides the probability of fracture, and it breaks, it fails. Okay, this happens. Then you go above, you will have more amount of plasticity happening. So amount of plasticity is increasing as you increase in temperature. Okay, you don't find dimples or anything in this unless you go here in this region. In this region you have a lot of ductile crack happening, crack growth happening, and after that fracture happens, brittle fracture happens. Okay, but here in this region you will not see a lot of dimples in it. But in a broken sample, what you will see is, so for example, if this was your fatigue pre-crack, okay, until here you have fatigue pre-crack, and then you had fracture, so you will see something like this, very small, and then complete fracture. Okay, so you will see river lines and all these things here. Okay, so this is a representation of plasticity. This is happening when the crack is either blunting or there is some plastic deformation. Okay, and this size is exaggerated. I'm showing you a very unrealistic picture of this. In reality, it will be very, very small. Even in a scanning electron microscope, it will not look that big. Okay, but as you increase temperature, this thing will increase. Okay, so this is called stretch zone, and the size of that is measured and called a stretch zone width. And this has been correlated with the fracture toughness in ductile to brittle transition. So this area is open even now. For example, in brittle fracture, we don't have any signatures to correlate with fracture toughness. It doesn't mean that there is no signature. It might be that people have not found it. So this area is pretty much open for research. Okay, and it's just that you find something and you think in certain way, and then you can probably correlate with the. So a stretch zone width, for example, will not work if you don't have a crack to begin with. So that's a special case. If you are just breaking tensile sample, you might not have something like this. Also in very high cycle fatigue, so when we do fatigue cycling, we see striations, right? And then endurance limit and all those things we'll talk about. But there is a region where you go to more than 10 to the power 9, 10 to the power 10 number of cycles, which is not in the books. Okay, so that regime is called very high cycle fatigue or giga high cycle fatigue. And in that region, you don't see striations as such, and the crack does not develop from surface. For fatigue fracture, the signature is that the crack will develop from the surface, always. Okay, so when you do testing of that, the mandatory thing is that your sample must be mirror polished, your tensile sample. You should not have surface roughness, a lot of that, because that will create error. Depending upon how much surface roughness you will have a fatigue crack initiating from an early stage for different samples. So you need to polish it to the same level as others are doing. Okay, but in a very high cycle fatigue case, the crack develops from inside, not from outside. Why? Because the damage has been happening for all the duration of 10 to the power 10 number of cycles. It would have failed in 10 to the power 8, 10 to the power 7 number of cycles if the load was higher. Okay, load is smaller, and the concept of endurance limit said that you can go to infinite number of cycles and things will not break, but that's just stupid. That cannot happen. You are supplying energy to the system. System cannot just keep on growing and evolving. So the damage does get accumulated, and then it doesn't come on the surface, it breaks from inside, and there they have found a different fracture surface signature, which is called fisheye. Okay, and the work of Murakami and Mugrabi, Hale Mugrabi, that you can follow. If you want to write that report, you can do that. So there are different cases where fractography has been very helpful in understanding either the concept of how the failure happens, or in finding out in the components how the component has been. Okay, good then.